Acyl anion equivalents are one way to make alpha hydroxycarbonyl compounds. Another way to make alpha hydroxycarbonyl compounds from aldehydes is to use thiazolium salts. Generate something which acts like an acyl anion. A thiazolium salt is formed by treating thiazole with an alkyl halide and an alkyl halide that's often used because it allows that belongs in the wrong spot. This is thiazole. And nitrogen and sulfur in a 5-membered ring. And the SN2 reaction will occur to put a long chain on the nitrogen. Thiazole is not particularly organic soluble as the salt. That as the endodecyl compound endodecyl thiazolium bromide is soluble in organic solvents. The pKa of the hydrogen between the positively charged nitrogen and the sulfur is substantially more acidic than the pKa of the hydrogen for the 1,3-dithiazole, where it is sandwiched between two sulfurs. One, because of the greater electronegativity of nitrogen, and two, because of the positive charge on nitrogen. It is resonance stabilized when the hydrogen is removed, and that hydrogen can be removed by alkoxide bases because it's enough more acidic, or by hydroxide even. And we'll just call that R now. To form an anion, which is resonance stabilized, but not by taking the negative charge and distributing it, because we already have tetrasubstitute nitrogen, we can't make 5 bonds to nitrogen, but by spreading that pi bond out onto the sulfur and putting a lone pair on the nitrogen. So we have a resonance stabilized anion. It would also be possible to draw a resonance structure that looked like a carbene, where you have an unfilled octet and a lone pair on the same atom, neutral carbon in this case. So this anion is a reasonably good nucleophile and can add to aldehydes propanol, for example. So we have a deprotonation. Followed by our nucleophilic addition. Followed by our proton transfer. To form a new carbon-carbon bond to the thiazole ring. And preparation of these thiazolium salts is quite straightforward by simply taking the thiazole, which is commercially available, and treating it with the appropriate alkyl halide. This hydrogen is particularly acidic because it is now in an allylic position, as well as having an electron withdrawing hydroxyl group on it. In fact, it has a pKa very similar to the pKa of the thiazolium hydrogen in the first place, somewhere in that 17 to 19 to 18-ish range. So it can be removed. And pushing a pair of electrons onto nitrogen. You'll recognize that that proton is the one that used to be the aldehyde hydrogen. So the resulting anion will effectively be an acyl anion equivalent. And the product is an enol, but it's a especially stable enol. Because of the resonance. That acyl anion equivalent can add to a second molecule of aldehyde. I'm showing it from the resonance structure that has the negative charge on carbon, but you could just as well show the mechanism from the resonance structure that has the double bond, and neutral nitrogen, simply by pushing this electron pair in. The double bond will then move over. So either way you choose to show the mechanism, you would generate the same product, and the new carbon-carbon bond that's being formed here is between one of the aldehyde carbons and the other aldehyde carbon. Have our new carbon-carbon bond, we effectively couple the two aldehyde carbons together, which is normally difficult to do because both of those aldehyde carbons are partially positive. Proton transfer reaction will yield a diol. of those alcohol hydrogens are sick, so it's possible to remove this one. From that 1,2-diol. And you'll recognize that that looks a lot like the alkoxide ion that was formed through the initial addition of the thiazolium salt. And since that step was reversible, we can regenerate the carbonyl compound to generate our alpha hydroxy ketone. And regenerate the thiazolium anion. Where it can go back in and add to another molecule. So it only requires catalytic quantities of the thiazolium salt. But because most of these steps are equilibrium, it's limited to coupling of two of the identical aldehydes. To generate a product that's kind of symmetrical, that has the same substituent on the ketone side and the alcohol side of this alpha hydroxy ketone. So it's useful because of the unique acid-base properties, first of the thiazolium hydrogen itself, the hydrogen between the nitrogen and the sulfur on the original thiazolium salt. And then second, because of the hydrogen on the aldehyde, after we form that new carbon-carbon bond to the thiazolium salt, the hydrogen that used to be here is particularly acidic by virtue of the ability to resonate, to generate a neutral resonance structure where the pi bond here, the carbon-carbon pi bond, is in between a nitrogen lone pair and a sulfur lone pair. So there's lots of possible resonance structures. You can imagine even drawing a resonance structure where the double bond is to the sulfur. So that resonance stability of this anion causes it to be stable enough to form where an acyl anion is normally not stable enough. There is an important biochemical analog to this, a thiazolium salt. That is an important enzyme cofactor for enzymes within the tricarboxylic acid TCA cycle, and that is vitamin B1 or thiamine. And it's a thiazolium salt. often you'll see on multivitamins that it's introduced as thiamine mononitrate. Thiamine mononitrate has this structure. There's the acidic hydrogen there. And we've got a hydroxy ethane on position against the sulfur, got a CH3 over here next to the nitrogen, and then this pyrimidine ring, two nitrogens here attached. The active enzyme cofactor has a diphosphate on here. And that compound is thiamine pyrophosphate or thiamine diphosphate. In the old literature, you'll see this group here called pyrophosphate, often PP. And so you'll see that PP on a lot of enzymes, a lot of enzyme substrates like dimethyl pyrophosphate, DPP, or isopropanol pyrophosphate, IPP. And the modern literature refers to this as a diphosphate rather than a pyrophosphate. So when you see diphosphate or pyrophosphate, those are the two. So thiamine, since it acts inside an enzyme active site, is not limited to coupling with the enzyme anyway. It's not limited to coupling two identical aldehydes because you can arrange within that active site to put the aldehydes in the right orientation. That one aldehyde is close to the hydrogen that's removed from thiamine, and the other one is going to be close to the new anion that's generated after that first carbon-carbon bond is formed. So the thiazolium salt that we use is a simpler version. Right? It has just a regular alkyl chain on here instead of this pyrimidine ring. But the mechanism of operation is the same. And in both cases, the purpose is to take the aldehyde hydrogen and render it acidic enough to be removed by a base to form something that looks like, well, that doesn't look like an acyl anion, but behaves as an